Hello and welcome to this live Q&A. This is the next instalment in a whole series of live Q&As that we're doing as part of the Oxford Sparks Science at Home campaign. If you're new here, then why not subscribe and keep up to date with all of our latest content. If you're not new here, then welcome back. It's really great to have you here. And if you're not following us on Facebook, Instagram and Twitter, please do so. We're at Oxford Sparks. So today I am delighted to be joined by Dr. Tom Crawford. If you don't recognise that name, then you might recognise the at Tom Rocks Maths YouTube channel. So today we're going to be chatting about everything from maths itself to maybe some maths tattoos, maybe some things about how he got into doing these YouTube videos. So hello, Tom.
Hello, Fiona. Pleasure to be here. Hello, everybody joining us for the chat. So should we get straight into it, or do you want me to tell everyone a bit more about myself? I think you've done a great job with the introduction.
Thank you. A bit of both, really. So yeah, it'd be great if you could just introduce yourself in a couple of minutes, maybe introduce your research area. What do people need about you?
Okay, perfect. Well, I think you started with the key thing, which is I am a mathematician here at the university, here in Oxford. I'm currently in my office where I teach, hence my blackboard. I live in the same building as my office, just to confirm. I am not
There's no
breaking any rules
here. Yeah.
No, absolutely not. And as Fiona said, I also do lots of mass communication, sort of science communication work through Tom Rocks Maths, which is my online platform. So at Tom Rocks Maths, tomrocksmaths.com. It's a whole thing, sort of a bit of a theme going on. And what I try to do is I try to teach maths or talk about maths, but I try to make it as fun, engaging, exciting as possible. So I remember myself, most maths lectures you go to, whilst they get the content across, often they're not the most exciting things, shall we say. This is potentially true for most lectures. So I try my best to still present quite complicated material sometimes, also some simpler stuff, but sometimes I am tackling university level maths, but I'm trying to get excited about it and present it in interesting and new, unique ways.
Yeah.
And then my actual research was in fluid dynamics. So my PhD was looking at the movement of fluids. This is the field of fluid dynamics. I should mention at this point, when we say fluid in the field, we actually mean anything that changes shape to fit the container that it's inside. So this often gets people, because you think fluid, you know, naturally you would associate that with a liquid, but for fluid dynamics, this includes gases as well. It can even include some solids. So, for example,
ice? That's my question.
What was that? Sorry.
Does it include ice?
Yes, that was exactly what I was about to say, because someone, I think you work in that field, right? So that's why you're probably thinking about ice and whatnot. So so if you see a time-lapse video of a glacier or an ice sheet, for example, where you're watching it over a period of months, but then you speed it up, it literally looks like a river flowing down a mountain. And so it does actually behave like a fluid in that sense. Obviously, you slightly modify the equations a little bit for something like ice, but they still work, and we can still model and understand this. And the particular question that I'm interested in is sort of, where does river water go when it enters the ocean? So we're looking at the interaction between river water and ocean water. And the main motivation for this study, beyond it being incredibly interesting mathematically from a fluid dynamics perspective, of course, is that, of course, the oceans are pretty polluted. This is a reasonably well-known sort of fact. And we want to do a better job of cleaning them up, making them better. And a lot of the pollution, in fact, 80% of the pollution in the ocean comes from land-based sources. And most of this is entering the ocean through the river system. So if we're able to understand what happens to that river water containing the pollution, if we know more about how that spreads in the ocean itself, then we can figure out which areas are most susceptible to pollution. And then when we try and clean things up and try and combat the problem, you can then focus your resources on those particular areas. So ideally, we'd clean up the whole ocean, right? That would be best case scenario. But obviously, unfortunately, we don't have the time and resources, right? It's just not going to happen, right? So you have to think of other ways to do that. So you want to maximize the resources you have, so we can focus on the areas where the river water goes, because that will be carrying most of the pollution. So that's the big picture question. I can go more into the nitty gritty details if we like. I could even draw a little diagram.
Well, this is probably a good point for me to just interject and say that the brilliant thing about us being live is that you can ask questions. So if you've got a question for Tom, if it's about the fluid dynamics things we were just chatting about, or something related to his channel, then please do send them in. I can see, and I'm not just rudely looking away from the screen, I'm keeping an eye on the questions, that we already have a couple. But maybe you could just go into a little bit more detail about that. I personally want to see a diagram.
Yes. I mean, I've got the blackboard, so I might as well use it, right?
Exactly.
Okay. So I was saying we're looking at rivers flowing into the ocean. So you want the picture you have in mind, and this is an idealized setup, right? I'm not going to go too testing with my artistic skills. So this is going to be the land. This is your river. And this is also the land, right? And this is going to be the coast. Mm-hmm. Now, in the northern hemisphere, because of the direction of the Earth's rotation, when the water enters into this ocean, so I should label this as ocean. When the river water enters, the Coriolis Effect, so this is the sort of invisible force because the Earth is rotating. It's one way to think about it. It's why when water shoots from a sprinkler in your garden, it doesn't go straight. It has a bit of a curve to its path because of the rotation. So this force means that when the water comes in, it actually turns to the right. And this is true in the northern hemisphere. In the southern hemisphere, it will turn to the left.
Sure.
And now it's important when I say left and right, this is not north, south, east, or west. You want to ignore your compass points, because this doesn't matter whether this is pointing north or south. It's to do with left and right in the sense of, imagine traveling down the river. So you're like floating along in your boat. And when you get to the end and reach the ocean, whether you're traveling north, south, whatever, when you get to the end, you will be pushed to the right. So that's the picture to have. You need to literally be traveling down the river, and you will turn to the right in the north, left in the south. And then what happens, what we saw in my experiments, and then we did some field work. I actually got to sail around the sea for 6 weeks on a boat, which was both fun and also really boring, being stuck on a ship for 6 weeks. So it forms this really large sort of whirlpool region near the river mouth. So it's coming in, it's turning to the right-hand side, and you get this really large, just think of it as like a giant swirl. The technical term would be a vortex, but whirlpool, big swirly mess, they're all the same thing. So it comes in and sort of forms.
You get in sci-fi films.
Exactly. And then you also then get a coastal current which flows down here. So the river water enters, the Earth's rotation creates this Coriolis force, causing it to turn to the right. And as it does so, some parts of the water remain in this large whirlpool, but some parts escape and then continue to move to the right and continue along the coast. So in the context of pollution, there are two key things here. First of all, a large amount of the pollution will be concentrated around the river mouth. So this is really good news, because it's always the same area, right? For a bigger river, it's a bigger area, but we can just smash this with cleanup, and that's great. That's like a really good way of attacking the problem. And the issue is this bit that goes along your coast for two reasons. So first of all, most people live along coasts. They are nice regions of the world to live in, and so the water is actually most polluted along the coast in general. So that is sort of the first issue. And then second, this is trapped. Water in the whirlpool is trapped, but the water here can sort of escape, and like you can think of it as like escape out or bleed out into the rest of the ocean. So this bit is kind of the issue, because this will start to propagate and spread the pollution further and further away from the original source. So this is trickier to manage, and this is kind of easier to manage.
Yeah, makes sense.
So that, in short, is sort of the basics of the river outflow and how water moves. And we can then, I can go into more detail about the exact maths of it, but I'm quite keen to take some questions. So
yeah, if you have questions about this, please do send them in. It's so interesting, and I really love hearing about this because I think, there's a lot of people sat in maths lessons at schools thinking, how can this ever be applied in the real world? And actually, it's things like this, and it's things that we might not even have thought of. So yeah, it's really great to hear. I'm wondering if I should just dive straight in with this. It was a question that came in within seconds right off the bat. As for the later questions, keep it clean, people. Keep it clean. So first one, you're pretty well known for stripping off while explaining maths to people. Have you ever stripped down beyond your boxes in a mathematical way?
Well, I guess I can kind of say yes and no. So perhaps no, I have never done a video where I actually... So in the videos, I sort of strip back the layers of an equation. And like I said, to try and make it a little bit more fun and exciting, I happen to strip back myself. And I should also...
if people explained that. For people who don't know, I'm glad you offered the explanation, which I...
Yeah, I don't just always do maths in my underwear. It's meant to be a bit of fun. It's meant to be a bit of comedy. So like in the videos, it's suddenly I'm talking about layer 1, and then I just like cut, and I just don't have a shirt on. I'm like, oh, we're on layer 2 now, and then I carry on. It's nobody actually wants to get undressed on camera. Like, at least I definitely don't. It's more about, it's a bit of fun, just something different. So first of all that, but then, so yeah, I tend to pick equations on purpose that have 4 or 5 layers of difficulty that I can strip back. And then I wear the appropriate layers of clothing so that I end up in my pants, in my underwear.
It has been very thought out. Yeah.
Yes. But then the other part of the question is, I actually recently took part in a maths photography exhibition, and I exhibited some of my tattoos. And when I was doing the photo shoot for the exhibition, I actually have some tattoos where to make the photo look better, had to basically fully strip. So obviously these were done artistically, and this was all safe for work. But
very tastefully, in theory, I'm sure.
I have to strip down completely.
I didn't even know there were such things as mathematical photography exhibitions. So that's pretty cool. Should we go to the tattoos now, seeing as they cropped up naturally? I can see some. Do you want to tell people? I know you've got maths ones, which is pretty cool. Many
maths ones, yeah. Well, seeing as I was talking here about my research, so I can start with, hopefully everybody can see this.
Yeah, we can see that.
Okay, so we have a formula here, which I will also write on the board. So it says h divided by h naught equals 1 minus alpha t, or 1 minus alpha. Okay. So this tattoo is on my arm, and this was according to my examiner in my PhD, this was the key result of my research. I didn't realize this myself, I will be honest, until the examiner told me, and then it became apparent that perhaps it was. So this relates the depth of the vortex. So here I've shown a bird's eye view, but of course the vortex has a depth. So if this is the vortex depth, h, then h naught is its starting depth. So we usually label things with a subscript 0 to show that it starts at t equals 0, like the start of the measurement.
Yeah.
So this is the initial depth. This is the depth that changes. And then this relationship, this alpha parameter, so this one, I've actually missed off a letter. The alpha I, the term here, this is your initial vorticity. Mm-hmm. So when I drew my picture of my whirlpool, I said that you can sort of measure the strength of that rotation, the strength of the vorticity. You can measure that, and that is labeled alpha. So again, this is your initial depth, initial vorticity, so initial strength of the rotation. And then this is the depth changing over time, and this is the change in the vorticity over time, which is why it has the T. Mm-hmm. And so this relationship I verified this with experiments and derived it mathematically, and it was slightly different to what had been seen before. So previously, this term wasn't there. So we just had 1 over 1 minus alpha I in the previous situations. But in my experiments, if that was true, that would say that the depth was constant, because it would be depth over constant equals constants everywhere. So depth would have to be a constant. But in my experiments of the depth, so if this is time and this is the depth, h. So if it was constant, it would just look like that, wouldn't change. But what I saw was a very, very gentle sort of decrease in the depth. It wasn't quite a straight line, but there was a decrease in my data. And so I had to try and explain this. I did lots of experiments, kept getting the same thing. And so I figured maybe it's actually our sort of formula needed modifying. And that was what led me to do that. So that was
We've had a comment, which is that you've kind of given yourself the ultimate crib sheet and the ability to cheat in exams. So we're wondering what invigilators might have to say about that. But
well, I actually know this because somebody, I've been asked this many times by students in particular, because for example, I have a set of equations, the Navier-Stokes equations, tattooed here, which are the main equations of fluid dynamics, and you, like, as part of an exam, even here in Oxford, you would probably need to know these equations, right? And that could, in theory, be an exam question. So I believe the rules are that if you have a tattoo of something which is part of the the course, then you have to cover it in black tape.
No way.
So
they thought it
declare
through.
it to the examiners, of course. You could just not declare it and maybe get away with it. But if you were to declare it to the examiners, then it would have to be covered in black tape, and they would have to check this before you entered the room, to make sure you weren't cheating.
Makes sense. So we had another question in, which is kind of linked to what you were talking about. So you kept mentioning your experiments, and Michaela was wondering, have you ever tested your model in the real world? So how do you actually go about looking at these things experimentally?
Very, very good question. So first of all, the idea of the experiments, and this actually took the first sort of year and a half, nearly 2 years of my PhD, was thinking about how can we recreate the real world situation realistically in the lab. So when we initially tried to do this, the main problem we had was we had a supply of water sort of coming out of a pipe, but because pipes tend to be quite small, the water would shoot out like a jet. Whereas in a river situation, like, this doesn't behave like a hose pipe. It's very, very sort of slow and plodding compared to this jet-like behavior. So that was the main issue, was sort of figuring that out. So we did think a lot about that in designing the experiments. But then, of course, you still need to test this in the real world. And so I was fortunate enough, I had access to some data for the North Sea. So there was it was called the North Sea Project, very original name, which was done in the 1990s, where basically they had a ship, and it just sort of sailed in zigzags all around the whole of the North Sea over the period of several years, making measurements everywhere of various different properties of the ocean, depth, temperature, density.
Yeah.
And I had access to that data through my, because that was with the research council who was funding me, etc. And so I could use that as a starting point. But then I also actually got to go see myself, like I mentioned, and this was kind of by chance. This wasn't really planned as part of the project, but somebody else in the fluids group in Cambridge was going on a research cruise to Antarctica.
Cool.
So, which is awesome. And I wanted to go along on this. And it just so happened that I actually had a very convincing scientific reason to also join the cruise. So they were going to study, something slightly different. They were sampling various things. They were kind of sampling large vortices or large whirlpools. They were sampling those in the Southern Ocean, so the big ocean around Antarctica. And that was for climate model purposes. But they had some spaces on the ship for extra scientific projects. So with my supervisor, we put together this sort of application for me to join, saying that whilst Antarctica has no rivers, of course, it does have very large ice sheets. And at the base of those ice sheets, you have the meltwater. So because of the friction of the ice sheet sliding over the rock, it will start to melt, and it creates sort of almost like underground streams. And these eventually leak into the ocean. So we wouldn't call them rivers in the sense of like the River Thames, for example. But it's still, I have fresh water, which is lighter than the ocean water, entering the ocean. So I've got light water entering into heavy water.
Yeah.
So it's still the same physical setup, same foundations as a river entering an ocean.
It sounds a legitimate reason to go on the Antarctic expedition.
Exactly.
So don't worry.
So we went, and I managed to get some really nice measurements, and sort of it did more or less show this kind of pattern. So obviously we couldn't really measure the vortice, the large like whirlpool bit, because we didn't know where these streams appeared, because they're sort of hidden underneath the ice, and we couldn't go that close, and for safety and various things. But we did see a very distinct coastal current. So there was a very clear layer of fresh water around the coast in certain areas of Antarctica, which would suggest, could even use that, in fact, to locate some of these outflow streams from under the ice based on the fresh water being there.
I'm quite biased because of my own research area, but that sounds seriously cool. And I'm curious. So did you sailed around the whole continent or part?
Not quite. We kind of did like various figure eight patterns. So we were at sea for 6 weeks, started in the Falkland Islands, then sort of did round various patterns. The funny thing about the voyage was the main purpose was this other project. It was called Smiles. Great name for the project. And as I said, they were looking at climate models. And to get the particular data they wanted, you actually needed to take samples following a storm. So the Southern Ocean is the stormiest ocean on the planet. Yeah, exactly. So not only were we in the stormiest ocean on the planet, we were purposefully chasing storms in the stormiest ocean on the planet. This
is ludicrous from someone who's been there. That's insane. But I like the commitment to the cause.
It hit 2 force. So I think the scale goes up to 12. Am I correct for the storms? I think, and we hit. I think we had a force 10 and a force 11.
Yeah, that's pretty bad. Pretty bad. So I hope your stomach is nice and strong.
Well, it wasn't so. I did have a period of seasickness. I think everybody at some point had a few days of the seasickness. But the thing that really got me, and it's entirely my own fault, was on the in the cabins. So we had our beds. The beds came fitted with seatbelts, which in itself is a bit crazy. Like, why, you think, why does a bed need a seatbelt? This is just going to be uncomfortable to sleep in. And then, so I wasn't wearing my seatbelt. This was like a week or two in, because nothing that bad had happened yet. And I thought this is a bit over the top. But then obviously that was the night when the first big storm hit, and I was actually like thrown out of my bed, hit the wall on the side of my cabin. Just like awoke on the floor, like, oh, okay, that's a storm. And then did wear my seatbelt, my bed seatbelt, for the rest of the trip.
I was going to say, you learned through that, I'm sure. So
it's entirely my own fault. Like, we were told wear your seatbelts in bed, and the next day I was asking anybody else if that happened, and they were like, no, we slept fine.
We all wear our seatbelts in bed, obviously. That sounds really cool. And again, like, you might not necessarily have thought through mathematics that you get to travel somewhere like that and do that kind of expedition. So for anyone at home thinking, where will maths take me? It could take you to Antarctica. Okay, I have a question. We might just need to step back a bit because I digressed about seasickness. From Crave5885, hello. Does this effect lead to any landforms, and are there any examples? I don't know if you can interpret that better than me, I guess, in terms of the water motion.
Yeah, the way I would interpreting this, like you say, could be incorrect, but I suppose in the context of a river with a very large amount of sediment, so the sort of, let's take something like the Amazon River or the Mississippi, flowing down to the US. Both of those have very, very large amounts of sediment in the river. And there are really nice satellite images. You should totally go and Google like satellite images of the Amazon. You can see it all coming out. And it looks like this. You see it turn. It's amazing.
Yeah.
But So if it's carrying lots of sediment, then of course you will actually see formation of sediment deposits centered on one side versus the other, depending on where you are in the world.
Mm-hmm.
So there are absolutely very clear examples of this. I think there's a river, the one that I usually talk about, it's called the Burdekin River in Australia. And it's very, very obvious that because we're in the southern hemisphere, it will turn to the left. So as the river flows out, there are you get these mountains of sediment all along the coast, and you can very clearly see the way that the water is going in that direction, but not the other way. So for rivers with large sediment content, you can indeed spot this behavior of left and right. Absolutely.
That is really interesting. Yeah, I'm definitely going to go look that up now. Okay, so the same person has asked an unrelated question, but I feel it would be nice to ask it. Favorite Pokemon?
Favorite Pokemon? Well, I have the Pokeballs on my arm.
I think that's probably
the fun story here is I have the two. So I have the really realistic one, and then I have the old school pixelated one from the Game Advance one that I played as a kid. Because I couldn't decide which one to get, so my tattoo artist convinced me I should get both. Because why make a decision when you can have everything?
A rule for life.
So I have those two, and then I actually have two Pokemon tattoos on my leg, which I unfortunately can't show you. My jeans are too tight to roll up, but I have two Pokemon tattooed on my leg. Because again, I couldn't pick a favorite, so I got my two favorites from the original, which would be Butterfree, the little butterfly one, and then Zapdos, which is the electric bird. So they were always my two favorites. Again, when I played as a kid, and I still play now.
There you go, Crave 5885. Favorite Pokemon's done. Well, I was going to move on to another maths question because this half hour has just flown by. But just before we move on from tattoos, which is your favorite and which is your least favorite? I'm not sure the least favorite is a fair question, but
well, I honestly don't think I have a least favorite. So at the moment, I think I have 56 last time I counted. Now at the moment,
whoa, that's a lot.
Yeah, I mean, you obviously can't really tell. I'm just wearing a t-shirt and my back. There's many cartoon and video game characters. I've actually been posting pictures of some of them on my social media. So
there you go. Follow. It's at Tom Rocks Maths for all of them, so you can check them out.
So I don't think I have a least favorite, but in terms of favorite, it kind of changes. So I really like the two Pokeballs, but they're quite recent, so I think you have that recency bias. And then, like I said, I've got lots of video game and cartoon characters on my back. And I really like those, especially because one of them, Crash Bandicoot, it's like an old school PlayStation video game. I've literally spent my entire childhood playing all of those games. And my tattoo artist, like that's basically his specialty, is doing video game characters. Like each artist has their own particular thing they're sort of really into, and that one definitely is on my Instagram. That tattoo is by far like the best tattoo I've ever seen. Again, I'm obviously biased, but I think that is probably my favorite, just because the detail and the quality is just incredible.
Good answer, and I think also good answer to say that it varies, because I mean they're there now for life, so you want to
exactly. I forget half of them are there sometimes as well, because it's not often you sort of see like the backs of your thighs or your back even, really. So
yeah. Someone can compliment you and then you'll be like, yeah, I've got that one. I forgot.
Oh, yeah.
Cool. So I want to ask, as not often am I speaking to a mathematics professional, what is your favorite number? There are many to choose from.
This is great, because this also leads into tattoos, because it's tattooed on my arm.
No way.
That is my favorite,
to be honest, but yeah.
So I think the best way to explain my favorite number is going to be for me to pose a little bit of a puzzle, a bit of a question, in fact. And then if we go through this, then I think you will see why it is my favorite. That's the idea. So I'll just clean the board.
You're making me wish that I had some sort of whiteboard or blackboard in my house. I know this isn't your house, but it would be so handy.
So I prefer chalkboards, but the dust is a nightmare. I can just... you have to be... Well, I'm having to like wipe it and wet it and everything. So I'm going to propose to you the following... I'm going to pretend this is like a game. game show, and you have the choice between 4 prizes, shall we say. Okay. So your first choice, option A, is you can win £3 right now. Take home your £3. This is a budget game show. And option B is you can have £1, but for the next year, I will give you 1/12 interest every month.
Okay.
So it's kind of like an investment, and that's for 1 year. Then option C.
Can I just say, it would be really good. I don't know if you're about to ask people which they'd like, but it would be awesome to get like in the comments what people think about this as we go along.
That was exactly what I was going to do, yeah. And then we can have £1 plus 1/52nd interest every week for a year. And finally, option D, why not do £1 plus 1/365th interest every day for a year? And I want to know, which one do you pick?
Okay, guys, in the comments, vote.
Yes, I will clean the rest of the board whilst you're doing that. So which one do we want? Let's do it in pink.
Can I ask a question that's about the Coriolis effect that just came in while we wait? I know we're asking people to cast their minds back a little bit, but Martin wants to know whether hurricanes, so air forces, are also affected by this force, and if so, can they cross the equator, or does that act as a kind of natural barrier?
Ooh, that's a great question, actually. So the first part, absolutely, they are affected. So this kind of leads into the myth of the water in your sink going in opposite directions.
I almost asked about that earlier. Yeah.
Yeah, and I will emphasize that one is a myth, right? So there's a very, very important sort of subtlety to the Coriolis force. So the way I like to think about it is, right now, us as humans, we do not feel the fact that the Earth is rotating. Right? We know it is, because otherwise, I guess everything would just like end and blow up, and who knows what would happen. So it is rotating, but we don't feel it. And that's because we are tiny compared to the size of the Earth. But a river is much longer. It could be hundreds of kilometers long. And so the river is much more comparable in size to the Earth. So the river feels the rotation, and therefore that's why it behaves with this turning left and right. So with a hurricane again can be hundreds of kilometers across. When you see the satellite images, you perhaps don't realize when they show this, but that, you have hurricanes the size of countries viewed from above. And so they feel it, and that is why you get the anti-clockwise, I think, in the northern hemisphere, or is it clockwise? It swaps.
Yeah.
You always get this confused. It's right. So the right and left for the river is correct.
Yeah.
And you get this alternate rotation of the hurricane, one direction in the north and it flips in the south.
Yeah.
Now, as to whether the equator is a barrier, I honestly don't know. I've never thought about that, which is a really, really neat question. But when you're close to the equator, the effect decreases rapidly. So, for example, the Amazon River, going back to the river context, that's really close to the equator, because the Amazon, it's not quite the equator, but it's very, very close. And the Amazon river water spreads out equally in all directions. It doesn't really turn left or right because it's very close to the equator. And so the Coriolis force is really small. It's very weak. So similarly for a hurricane, I imagine they're probably going to rotate really, really slowly. And so maybe it would slow down its rotation as it moved to the equator. And perhaps if it passed through it, again, I don't know if it is a barrier or not.
It's interesting, isn't it?
It's a very, very good question.
And,
I'm sure perhaps a climatologist would actually know the answer, or someone who studies hurricanes. But from the mass perspective, you could see it working because it decreases. So even though you're still rotating in one direction, you're going so slow that you may as well be at zero. So you can see it possibly could change.
Yeah, interesting. No, thank you very much. It's good to get the maths input. Okay, so while we've been chatting, answers have come in. So let me just go through. We've got a vote for A, a vote for D, a vote for C, another vote for D, and 2 more Ds.
All right. So D is looking like the popular choice from the audience, but I'm glad we've got some variety in there because it shows that I can hopefully teach everybody something. So D is in fact the correct answer. Oh no, ignore me. A is the correct answer.
You were thrown by all the confidence from the audience for D.
I know. I was like, I just thought no. So this is good. So very well done, whoever said A. But everybody else, you're going to learn something. Okay, excellent. So the way to think about this is you can calculate exactly what B, C, and D should be. Right? We can basically do the maths. So for B, what we've got here is going to be 1 plus 1/12, and then we're multiplying that by itself 12 times because we're doing it. So it's 1 plus 1/12 of its value, and then if you then squared that, that would then give you the amount after month 2, and if you took it to the power 12, this gives you the amount after a year. You can sort of convince yourself this works by calculating the first few numbers, but this is the formula.
Okay.
And this comes out at, and I do have to check my working, this is £2.61 for B. So no one voted for B, which is good because B is the smallest. Now for C, same formula, but we've got 1 over 52, and we're doing that 52 times. So that one is £2.69. So that's 8 pence more than B. And then if we do it for D, 1 plus 1 over 365 to the power of 365, that one gives you £2.71. So D is better than B and C, but A, £3, is the winner. So what we're actually doing here is we're considering the formula. So here we've got a 12 and a 12, a 52 and a 52, 365, 365. So what we've really got is 1 plus 1 over some number, and then we take the whole thing to the power of that same number n. So for B, we've got n equals 12. For C, we've got n equals 52. And for D, we've got n equals 365. So these are just 3 examples of this formula. And what we want to do, or what might be interesting to do, is to say, well, these are increasing as I increase n through these 3 examples. But what if I did this every second? So I think there are like 3 million seconds in a year or something of that order. So if I did £1 plus 1 over 3 millionth, but then did it every second for a year, what would that give me, for example? So if you did that one, so I'll just write, if you did it for every second, the answer would be £2.71. It'd actually be the same as what we got here. It doesn't go up. So it stops. So what we want to know is, for this function, as we make n larger and larger, so we're taking the limit as n goes to infinity. We're making n bigger and bigger and bigger. And you can try this by plugging in different values of n and see. It will never go past a particular number. And this particular number is 2.718. Look at my arm. 281. ... And it carries on. That's why I have all the digits. Like pi, it continues forever. And this is the number. And this number is my favorite number because of this awesomeness of this formula. And it's equal to what we call E.
A good argument. Not what I was expecting, but I can definitely understand now why that is your favorite number. Awesome answer. And I'm learning. Everyone needs maths teachers like you at school. This is great. So these things could go on all afternoon. How are you feeling? Are you happy for like one more question and then we'll wrap up?
I'm having a great time, yeah.
Cool. Well, people in the audience then do still keep getting involved. I should say well done to Crave 5885, who did get the answer right as A, so woohoo. I guess I just wanted to ask a little bit more then, going back to your kind of YouTube stuff, how you get the ideas for your videos. If there's anything in particular you've been up to recently, feel free to plug anything you want to.
Well, I'll get the plug out the way. So I've been recently doing a GCSE maths series with the Maths Appeal team. So this is Bobby Siegel and Susan Okereke. They are both high school maths teachers. Bobby also does various things for the BBC, and he has his own, what's it called? Monkman and Siegel's Roadshow. They travel around Britain and talk about science. It's very cool.
Cool.
But Bobby and Susan, so they're maths teachers. They actually teach GCSE maths in schools, and they created a podcast called Maths Appeal, talking through various mathematical topics. And then when I met Bobby, we decided that we should convert this into a video series. So basically, we filmed this last summer. And then now we finally got around to releasing all the videos. So we've been releasing a video every Monday on a different GCSE maths topic, where each of us presents a particular problem to do with that. So we've done like percentages, we've done travel graphs, distance, speed, time. And then this week we did volumes. So looking at volume, the 3D shapes. And then we want everybody to watch it, send in their questions, and then we're going to answer them. I'm doing a live stream every Friday where I answer those questions, in fact. Basically this again, but on a particular theme, shall we say, rather than a bit more open.
Not wildly flailing around to various topics. That's awesome. So
and then in terms of sort of ideas, I guess in general, the thing I try to do when coming up with something like this, for example, right? So this would be how I would explain to somebody what is E, what is Euler's number. Now, the approach, the maths, is actually just this formula. But my sort of thought process was, well, if I just give somebody that formula, like, okay, it's what they need to know ultimately, but there's just no real enjoyment to that. Okay, actually, I say this, I love that formula. But if you're a mathematician, maybe you also could get enjoyment out of just purely, here's this amazing formula. But, the idea of just sort of this budget game show that I came up with. So when I do this, for example, in a talk, because I often talk about this in one of my school talks or something, I actually have the money in a pot. And so the person who's playing the game show gets to pick, and whatever they pick, I will give them, £2 or £3 that they picked. So I think for me, it's just about the maths ideas are already there. So, it's Euler's number, it's E. And then it's just about thinking, how can I actually bring this to life and make people who might not like maths or might not normally want to do maths want to play? Because even if you don't like maths, you're kind of potentially or hopefully you're a little bit interested in which one of these is the one I should pick. Like, I want to win all the money on the game show. So it just turns out that to solve it, you need to do some maths. So I think that's the main thing I tried to do. I have my own idea of what I think are nice maths topics. And then it's just about trying to make it a little bit different, present it in a slightly unique way, and try and make it relevant, I think. Because this is a very abstract number. It's quite hard. Like, most people won't have come across E before. So I have to come up with a situation of our pretend game show that puts it into a context where they can appreciate the maths behind it.
Perfect. Yeah, that makes so much sense. As you say, it's all about making it relatable. It sounds excellent. So if you have enjoyed this today and you want to see more maths, then do tune in. It's 4:00 on Fridays. Is that right? For the
4:00 every Friday, yes.
Maths Appeal. Awesome. And if you've got questions in advance, where can people send them to?
Anywhere on social media. So just at @TomRocksMaths, Instagram, Facebook, Twitter, YouTube, TomRocksMaths.com. There's a contact form on my website. You can send me something in the post, however you want. Just if you write it somewhere so that I will see it, we will then try and answer the questions on Friday. That's the idea.
By any means possible. Love it. Wonderful. So I don't know. Is there anything else you wish to share with us, Tom, before we wrap up? Otherwise, it has been fantastic.
I think let's do a final. So I challenged myself to do something recently, which is for a video I'm currently editing, so it will be out soon, which was to explain the Millennium Problems in under 2 minutes. So I will start by telling you what the Millennium Problems are, and then I will try, and you can tell me if you want, whether I can mention them all in under 2 minutes. Okay, so the Millennium Problems, in case you have never heard of these, are a series of maths problems that were sort of put together. So the problems themselves have been around for a while, but the list of 7 Millennium Problems was decided in the year 2000, and these were deemed to be the most important unsolved problems in maths 20 years ago. And the Clay Institute in America had lots of money and decided they wanted to promote and encourage more people to go into maths and study maths. And so they said, we will give anybody who can solve one of these 7 problems, each one has a $1 million prize. Now, I first learned about this when I was a teenager, and I want to say this probably did play a role in me going on to become a mathematician. I've now realized that these are really, really hard. So I wouldn't say I'm trying to solve them necessarily, but it certainly motivated me, because who doesn't want, to do a math problem and get $1 million? It sounds amazing.
Yeah.
So the 7 problems on the list, right? So I'll try and do this quick fire. So the 7 that made the list. The first one is the Riemann Hypothesis. This one's pretty famous, but basically we have a function which we call the zeta function. Doesn't really matter what it is. It's a complicated maths thing. And what we think is when this function is 0, that is very closely related to where the prime numbers are on the number line. So prime numbers don't have a pattern. They're not like even numbers. They don't go 2, 4, 6, 8. There's no pattern to the prime numbers. You have to sort of test, can you divide, given 43, for example, you have to figure out in your head, well, is that actually prime? And so we think it's related to the zeta function. You get $1 million if you show that it is. Okay, the second one, P versus NP. So this is to do with computers. So we have 2 types of problem. We have the NP problems, which are things a computer can check the solution to quickly. So you set out your problem, whatever it is, and you give the computer a correct solution, or what you think is a correct solution, and very, very quickly the computer can say yes or no. So it can check the solution quickly. Then you have another set of problems called P, which are problems a computer can solve very quickly. So again, rather than giving it a solution, you give it the problem and it chucks back the answer super fast, right? Where we define fast by processing time and different things. And P versus NP asks, are these 2 problem sets in fact the same? So we think they are not. We think P does not equal NP. We think that it's possible to have a problem which is hard to solve but easy to check the answer to. But we can't prove it. So if you prove it, you get $1 million. Question 3 is the Navier-Stokes equations, my favorite. So I've already mentioned these. So they model the motion of every fluid on Earth. They work for physics and engineering setups, but mathematically, we just don't really understand them. They are very, very complicated equations because they're modeling so many different situations, solids, liquids, gases. So they're very, very complicated, and we just don't really understand them mathematically. So you get $1 million for that, for furthering our understanding. Then we've got the Yang-Mills mass gap hypothesis. So this is one to do with physics and talks about quantum field theory. We don't need to worry about what that is. The key idea here is physicists have a theory that they can show is true by experiments. So they can verify their theory, Yang-Mills theory, by experiments. We cannot prove it's true mathematically. So the job is, can the mathematicians write down the equations that agree with what the physicists see?
Got it.
In quantum field theory, get $1 million. The Hodge conjecture. This one is ridiculous because depending on which mathematician you ask to define it, you will probably get a different answer.
Intriguing.
It's very, very abstract. It's very, very complicated. In short, it says, given a particular type of equation, can I build the solution from simpler solutions to other equations? So I always picture the world being built from Lego. So when you build a building out of Lego, it's made from smaller pieces, which are the individual bricks. Mm-hmm. So this is kind of saying, is this true for this particular mathematical situation?
Nice.
Birch and Swinnerton-Dyer conjecture. This one is to do with what we call elliptic curves. They're just a particular type of graph. They're actually used in cryptography. And if you have an iPhone and use iMessage, your data is secured through elliptic curve cryptography. So super applicable area of maths. Like, it's actually used every day by Apple users. And this just asks about a way of checking how many solutions a particular elliptic curve equation has. In short, that one's also quite mathsy, but it has a really nice application. And finally, the seventh one is the Poincare Conjecture, and this one's actually been solved. So possibly the most exciting, because this one was solved in 2002. So it was solved very, very early on. So I think everyone got really excited, like, oh, now there's $1 million, we're going to rattle them off, all 7. And then 18 years later, there's still 6 to go. So this one basically said, if I have a shape which is smooth, so no sharp edges, it has no holes, and it doesn't go on forever, so it's finite, can I deform it into a sphere? So imagine having a blob of Play-Doh that is, that you can hold in your hand, and it's smooth, so no sharp edges and no holes. You can just sort of roll it together and get a sphere. But the Poincare conjecture says, is this true in any dimensions? So not just in 3D, but in 4 and 5 and 6 and 7. And we knew it was true in all of them except dimension 4. And the $1 million problem, which was solved, was, can we prove it in 4 dimensions? Which was done by a guy called Gregory Perelman, who is a Russian mathematician.
I was just going to ask. I felt he was due some credit. That's very impressive stuff.
And then, well, I don't know if this is the best or worst bit of the story. He turned down the $1 million.
Wow.
So he did it.
Vulnerable.
Yeah, I think so. He didn't really give any interviews. He's a very shy person, right? So this is all sort of speculation, but the theory is that he kind of, like, he didn't do it for the fame, because he was working on this before it was $1 million problem. He was working on this in like 1990, trying to solve it, because he thought the maths was interesting. So he sort of didn't really care for the money anyway. And then I think, again, the theory is that he didn't want the fame or the publicity, because when he actually released his proof, he just put it on the internet. He didn't even announce to the world, or or even publish it. He didn't even publish it in a journal. He just put it on the archive.
Wow.
And it's literally like the ultimate drops mic on stage and walks off.
Yeah.
So I think again, the theory is he didn't want the fame, but then how do you become more famous than the person who won $1 million? The person who turned down $1 million. So he's probably even more famous now, I think.
Yeah.
So
that's a great story. And also hats off to you for just reeling off those 7 without any hesitation.
It took longer than 2 minutes, I realized, but
that's okay though. We're here. I can't believe how quickly the time has gone, and I certainly found that really, really interesting. So thank you so much for doing that. I'm just going to check. I don't think we had any last questions in, because everybody was so interested in hearing you. So yeah, I mean, if you have any other questions, then drop them in the comments below, and then I speak on his behalf, but I'm sure Tom wouldn't mind going and just taking a look at those later if there was anything else burning.
If you want to send me questions, like I said, on social media, or in the post, message in a bottle, carrier pigeon, whatever, I will. Any means
possible. Wonderful. So that's fantastic. So yeah, send him your questions, subscribe to his channels, do check in to those videos on a 4 o'clock on a Friday to check out the GCSE Maths Appeal. And yeah, it's been fab talking to you. Thank you so much. I think one of your kind of taglines is maths, but not as we know it. And I can certainly say that that's been true today. So thank you so much. If you've enjoyed this and want to check out more content from us, then we are takeovers, live Q&As, videos every Tuesday and Thursday for the foreseeable as part of our Science at Home campaign. So please do get involved. If there's anything in particular that you would like to see, any particular fields you want us to cover, then please just get in touch. We are totally open to making this a conversation. So thanks so much. Do tune in on Thursday, where we will be chatting to Dr. William Glass from the chemistry department, all about his work. And in the meantime, stay safe, and we will see you soon. Bye. Bye, Tom.